All right, welcome back to this next video. As I mentioned in the previous one, the momentum of a system is conserved if the external force on that system, if the net external force on that system is equal to 0. Now, you have to figure out what system to include in order to figure out if the momentum is conserved or not. And basically, that's what we're going to do in this example and virtually the rest of the chapter, okay? We're trying to figure out what system and how much to include in it so that its momentum is conserved, and we're able to make useful calculations. So let's see here. You have a lab bench here, and we're assuming it is frictionless, okay? It's frictionless, and so there is no force due to friction. There is the normal force and gravity, but they are in the y direction. We're concerned about this x direction here. This is the x direction. And so our system consists of this object and this object, and there is no net external force on both of them. If I include both of them, the net external force is equal to 0, both horizontally and also vertically. We don't care about vertical. So what we care about is really horizontal, but in any case, the net external force is equal to 0. Yes, when they collide, this object will apply a force on this object, and this object will start to move to the right. And this object in turn will apply a force back on this object due to Newton's third law. And this object will either slow down and keep moving this way or reverse direction and move the other way. Okay? And our goal is to figure out, we're given the data here for object 1. For this object, we're told that it was initially moving to the right, and this is its position versus time. And then after the collision, our object reverses direction and moves to the left, and this is its equation, position versus time. Notice the object on the right, it was hit from the left, and it was initially at rest, so it only has one option, which is to move that way, because it experienced the force due to this one to the right. And this one experienced the force to the left. It was enough to reverse its direction. So our system will be this object plus this object, and their momentum as a total will be conserved, again, because the net external force is equal to 0. Now, so I will write down that the momentum is conserved. So use conservation of momentum. So our system will be these two objects. I'm not going to write that in words. Our system will be the two objects together. Since the net external force is equal to 0, then the net momentum is 0. The net momentum consists of the momentum of object 1 initially, plus the momentum of object 2 initially, and that has to equal to the momentum after the collision by conservation of momentum. P1 final plus P2 final, like so. And since it's in one dimension, I'm not going to write the vector signs. The momentum of object 1 will be the mass of object 1 times the speed of object 1 initially. The mass of object 1 is 250 grams, so that's 0.25 kilograms, times the velocity of object 1 initially. Well, we know that if you have x versus, this should say t here, just like that one. We know that derivative of position versus time will give me the velocity, so that is the velocity, the 0.75. 0.75 plus, now, the initial momentum of object 2 is 0 because its mass times its velocity will be 0. It's 500 times 0. So this part here is 0. Plus, not plus, equal the momentum at the end for object 1. Object 1, its mass is still 250 grams, which is 0.25 kilograms, times its velocity after the collision. Its velocity after the collision is to the left, and it's, look at this minus sign. So it is negative 0.221. Negative 0.21. So we're done with object 1. And then object 2 would be the mass of the momentum for object 2 after the collision will be the mass of object 2, which is 500 grams or 0.5 kilograms, times the velocity of object 2 at the end, v2 final. I don't know what it is. That's what we're trying to figure. So I think it's a simple calculation to figure it out. So you get v2 final will be, we have to use the calculator. Where is it at? Right here. And I'm going to go here. So I have 0.25 times 0.75, and then plus 0.25 times 0.21 divided by 0.5. According to my answer, it is 0.48 meters per second. And I'm going to just double check in the book that it is 0.48. That is correct. Okay, great. Awesome. So let's go to the next example. Here's the next example. Let's read it together. And let me stand here and read it. So it says, Bob sees a stationary cart from him. I think it's, I forget how many meters from him. I forgot that to write that down. Sees a stationary cart 8 meters from him. Cart 8 meters from him. Good. Got that. So it's 8 meters from him. He decides to run to the cart and jump on it and roll down the street. Bob has a mass of 75 kilograms and the cart's mass is 25 kilograms. If Bob accelerates at 1 meter per second squared, what is the cart's speed after Bob jumps on it? So here is Bob. Initially, Bob is not moving. Here's Bob. Here is the cart. Okay. It's 8 meters away. 8 meters. So Bob decides to start running. And we want to find the speed of Bob right before he jumps on the cart. So right before he jumps on the cart, what's his speed? So what is his speed right here? Well, I know that, let's call this step here step 0, step 1, and then after he jumps on the cart, you probably can figure what will happen. So the cart and Bob on the cart will be moving at some final speed. Okay. So we need to figure out his speed right before he jumps on the cart. So Bob accelerates. Why does he accelerate? Well, he pushes against the ground, so there is an external force on Bob, so his momentum is not conserved. We will worry about his momentum later. So there is an external force on him. And I know there is an external force on him because he accelerates. How do you accelerate? Newton's second law says you can't unless there is an external force on you. And so here is his acceleration. So we know that for Bob, v at step 1 squared minus v initial squared at step 0 squared is equal to 2 times the acceleration times x final minus x initial. Since I'm calling this 1 and 2, let me call it x1 and x initial. I'm just using kinematics. And so I want his speed there, v1 squared. His initial speed when he initially saw the cart was not moving, so that's a 0. Equals to 2 times the acceleration. The acceleration is 1 meter per second squared. And then x final minus x initial, the cart is 8 meters away from him. So the speed would be v1 squared is 16, 2 times 1 times 8 is 16, so v1 will be v1 will equal to just 4 meters per second. So Bob, right before he jumps on the cart, is moving at 4 meters per second. So after he jumps, so right here, Bob is still going like this, let me call it v initial now, that's 4 meters per second. Before he jumps on the cart, his speed is 4. Right after he jumps on the cart, I want to know. We wonder what it is. Now, before he jumps on the cart, and after he jumps on the cart, what's the net external force on him plus the cart? My claim is it will be 0, the net external horizontal force, because right before and right after, the amount of time is basically 0. And to apply an impulse, you need, remember, to change the momentum, you need to apply the force over a unit of time. If the time is so tiny, then right before and right after the momentum, the external force will basically be 0. And then the cart has wheels, so we're assuming there is no friction between the wheels of the cart and the ground, or basically frictionless. So anyways, we can use conservation of momentum. So we will say the momentum before will equal to the momentum after. Let me be more detailed. The momentum before he jumps consists of the momentum of Bob before jumping plus the momentum of the cart before he jumped on the cart. B for Bob, C for cart, and I for initial. That equals to the momentum of Bob after plus the momentum of the cart after he jumps on it. The momentum of Bob at the beginning is the mass of Bob times the speed of Bob before he jumps, V Bob initial. For the cart, that's 0 because the speed of the cart was stationary, it wasn't moving. Right before collision, it was not moving. Right before he jumps on it. The speed of Bob, or the momentum of Bob afterwards, will be the mass of Bob times the speed of Bob afterwards, and then the momentum of the cart will be the mass of the cart times the speed of the cart afterwards. But because Bob jumps on the cart and they move at some common speed, then the speed of Bob at the end and the speed of the cart at the end, they will have some common speed. It will be just V final. Their speeds, this and this, will be equal. So I would just call it V final and just factor it out. So it would be this. M Bob plus M cart times some V final. That's what we're trying to figure. And then here I have M Bob, V Bob, initial. And so we can write the mass of Bob is 75 kilograms. We're given that. The speed of Bob initially, when I say initially, please be careful. It's not initially when he first saw the cart. That was 0. He accelerated until he got to the cart and then jumped on it. That's what we're talking about. Initial is right before the jump, and then final is right after the jump. His speed after jumping, we calculated it to be 4. The mass of Bob plus the mass of the cart. Bob is 75 kilograms and the cart is 25 kilograms. Nice numbers. You just add up to 100, right? The cart is 25 kilograms, Bob is 75 kilograms. So we get 75 times 4, that's 300, and 300 over 100 is 3. So V final will just be 3 meters per second. And let me just make sure that I have that correct. And indeed, it is correct. It is correct. Okay, good. I hope this is clear. Let us go to the next one. Next one here talks about elastic and inelastic collisions. So we're going to talk about collisions properly. The first one that we're going to study is an inelastic collision, or perfectly inelastic. Perfectly inelastic means you have two objects. Let's say here is M1 with some V1 initial, and you have M2 maybe moving towards it with V2 initial, and then after collision they stick together, they just become a big mass, M1 plus M2, and maybe they move this way with some V final. They stick together and move at the same final velocity, at some same final velocity. Elastic collision is a collision. It's an idealization. I should say perfectly elastic here. Perfectly elastic, and this one is perfectly inelastic. Perfectly elastic is a collision in which both mechanical energy and momentum both mechanical energy and momentum are conserved. So right before collision and right after the collision, the momentum will be conserved, whether it's elastic or inelastic. Either way, it will be conserved. The problem is with energy. Energy is not, with inelastic collisions, the mechanical energy will not be conserved actually. And let's take a look here. Let's take a look here and we will see. So we have, so I ask you, we have two carts, they're moving towards each other, they hit each other, and then they stick together and then move at this common speed of negative 0.4 meters per second. And the answer is this elastic or inelastic? The answer is it's inelastic. It's perfectly inelastic because they stuck together and moved at this same common speed. And the question is, will they be, what was the initial speed of this mass here? This is mass 1 and this is mass 2. We will use conservation of momentum because the net external force to them will be 0. The fact that, again, this mass applies a force on this mass and this mass applies a force on that mass will be, it's an internal force and it cancels when we add the two objects together. That internal force will be 0 by Newton's third law. It will add up to 0. So we say the momentum before will equal to the momentum after. The momentum before consists of the momentum of mass 1 before the collision plus the momentum of mass 2 before the collision, and the momentum after would be the momentum of mass 1 after plus the momentum of mass 2 after. The momentum of mass 1 before will be m1 v1 initial, and the momentum of mass 2 will be m2 v2 initial. And then the momentum after will be the mass 1 v1 final. I would just call it v final because they stuck together and they will just have the same final speed. And then plus m2 v final, and as you can see, this always factors. You get m1 plus m2 times v final. And I want to find this out, so I have m2 v2 initial will equal to m1 plus m2 v final minus, I move this to the other side in order to solve for this one, will be m1 v1 initial. And yeah, let's figure it out. So we get, we will divide both sides by m2. Let me divide here. I'll just divide it out. m2 divided by m2, both of them. So we get v2 initial will be m1 plus m2 divided by m2. 200 grams, 400 grams, so that's 600 grams or 0.6 kilograms. M1 plus M2 is 0.6 kilograms. M2 is 400 grams, so that's divided by 0.4. And then V final, what's V final? V final is negative 0.4, negative 0.4, plus, oh, actually minus. M1 over M2, M1 is 200, M2 is 400, so 0.2 over 0.4. And then V1 initial, right? V1 initial here would be 3. And we need the calculator here, or maybe don't need. Let's see. We will just use it. It's easier. So I have 0.6 over 0.4 times 0.4 plus 0.5 times 3. I got negative 2.1. Negative 2.1 meters per second. So it's negative, which makes sense. We kind of assumed it was moving to the left. You don't even have to assume that. From the given information, you will figure it out. the numbers will just come out from the math that they're negative. And so negative 2.1. And before I go on, I want to show you that the mechanical energy is actually not conserved. In here, we're moving just horizontally. The potential energy didn't change. So we want to know the kinetic energy before and the kinetic energy after. Are they conserved? Let me get my calculator. The kinetic energy before collision is 1/2 mv squared for the first one plus the second one. The kinetic energy before collision will be the kinetic energy for mass 1 before plus the kinetic energy for mass 2 before, and it's equal to 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. And so that's 1/2 m1 is 0.2 kilograms and v1 initial was 3, so 3 squared plus 1/2 m2 is 400 grams or 0.4 kilograms, and then v2 initial squared. We just figured v2 initial, it's negative 2.1, so the kinetic energy initially. And so we get the kinetic energy initial was, it will be negative 2.1 any squared, it just would be 4.41 times 0.2 plus 0.9. I got 1.782 joules. What's the kinetic energy after? Okay, final would be 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. But m1 v1 final and v2 final will both be the same. They're just v final, and it's this number. So I'll just factor it out. So I'll just have 1/2 m1 plus m2 v final squared, and so we get k final will be 1/2 m1 plus m2, that's 0.2 plus 0.4. One of them is 200 grams, the other one is 400. And then v final squared was, or v final is negative 0.4, so 0.4 squared. And we get k final would be, and it would be 4 squared multiplied by 0.6 over 2, 0.048. So notice that the kinetic energy at the end is less than the kinetic energy at the beginning. So the kinetic energy or mechanical energy is not conserved in an inelastic collision. Momentum, however, is. Notice the criteria for conservation of momentum is that the net external force on a system is equal to 0. The criteria for conservation of energy, if you remember, what was it? It was the fact that you have only conservative forces doing work. And how did non-conservative forces sneak in? Well, they sneak in for this inelastic collision. For them to stick together, there has to be some bending or some interaction happens that is non-conservative. For example, if you have a car crash and the cars stick together, the cars bend, and it takes energy to bend the metal. It takes energy to break things, to break the lights, the headlights, and so on. So there is energy lost in that regard. Energy lost. It's lost to heat. It's lost to thermal energy. Now, if you include thermal energy, then the total energy will be conserved if you include heat into it. But we don't want to. Heat will be like a microscopic thing. Macroscopically in everyday life, we will just talk about the mechanical energy, and it's not conserved if the collision is not perfectly elastic. So I will pause this one here, And in the next video, we're going to talk about the ballistic pendulum, and it's a typical example you see, and it really tests you whether you understand when to apply conservation of energy and when to apply conservation of momentum, or both. It's a really nice problem that's found in every single textbook. And so we're going to get to that, and then we're going to talk about elastic collisions next time, and then we'll talk about the rocket equation, and that would be pretty much it for this chapter. All right, I will see you next time.